Okay, so for video number 2, we are going to be finishing up chapter R today. So on section R.6, we are going to be talking about factoring polynomials. So being able to factor polynomials is a big thing going forward. We won't do it all the time, but when it does show up, you need to be comfortable doing different techniques of factoring. So over the next little bit, I'm going to kind of run through some of the factoring techniques that you should remember from previous classes, and then maybe do a few examples along the way. So the first kind of factoring that you probably ever learned how to do is what's called GCF, which is just short for factoring out the greatest common factor. This is just a way that you can look at an expression and you can take out whatever is in common, and then whatever's left over you divide out, and that is your remainder. So for example, on number 1, when you have something like 4y to the 6th, 8xy to the 7th, when you're looking for the greatest common factor, you have to consider every single term. So in this case, what I mean by that is that you have a 4 and an 8. If you look, what's the biggest number that goes into both? That would be a 4. Since they both don't have x's, I'm not even going to worry about that term because you can't have a greatest common factor if they both don't have it. But if you look at the y's, the first term has 6 y's and the second term has 7, so I could factor out 6 of the y's. So then to get what's left over, you have to figure out, well, what's left over that you didn't factor out. You have 4y to the 6th, but you took out a 4y to the 6th. That means if everything comes out, you have an understood 1 left over. The 8xy to the 7th, if you take a 4 out of the 8, there's a 2 left over. We didn't bring any x's out, so I'll leave it there. You had 7 y's and you took 6 of them out, so there is 1 y left over. That is the idea of factoring with greatest common factors. So we're going to do a few more examples just like that. So number 2 and number 3 are very similar. So if you look at number 2, it says you have 5x to the 4th minus 30x cubed plus 15x squared. Well, if you're looking for your greatest common factor, you have the 5, the 30, and the 15, which all have a 5 that goes into all of those. So that's my GCF. You have an x to the 4th, an x cubed, and an x squared. So since you have to take out what's in common, they all have at least 2 x's involved, so I'll factor out an x squared. Then by figuring out what's left over, going from left to right, you had 5x to the 4th, but you brought out a 5x squared, so there's still 2 x's left over, minus 30 divided by 5 gives you a 6, and then x cubed with an x squared coming out leaves 1x left over. And finally, 15x squared, if you take out a 5x squared, there is just a 3 left over. And that is your final answer. Now, not only can it be singular terms, you can actually factor out polynomials as your greatest common factor. So if you look at number 3 down here, you have a 7x times x minus 5 plus an x minus 5. Sorry. Don't try to multiply all this out. That's not helpful. Instead, what I notice is that since both terms share the same polynomial of x minus 5, why don't I factor that out as my GCF? And then the terms that you didn't, so that's 7x, and then that understood 1 is what's left over. So you have a 7x, there's a plus 1, and that's your final answer. Sometimes, as we're going to see a little bit later on, is that when you're working on problems, it may end up in this kind of semi-factored state, so therefore you can continue the factoring by making it a greatest common factor. All right, so factoring by grouping, probably the least common type of factoring that you'll see, but I wanted to kind of run through it with you in case it does pop up. So on number 4, you have xy plus 5x minus 3y minus 15. So the idea of factoring by grouping usually occurs when you have 4 terms, and we're going to group them into pairs in the order in which they're listed. What I would do is I would factor out the GCF of both terms separately. So if you look at just the xy plus the 5x, you can see that both of those terms share a x in common, and that means you have a y plus 5 left over. On the second pair, negative 3y minus 15, they both share not only a 3, but they both also share a negative in common you can factor out. So if you take a negative 3 out of both of these terms, you have the y plus 5, and that's not a coincidence. That's why I showed you that GCF example. Since they both share the same parentheses, you can now do an overall GCF, which means you can factor a y plus 5 out front, and this x and this minus 3 is what's left over. So you have now factored your original equation into a more simplified answer. It is y plus 5 times x minus 3. And that's the idea of factoring by grouping. Let's do a second one so you can kind of see it another time through this. What if you have something like 3ab minus 2a minus 12b plus 8? So once again, I'm going to break it down into two parts. On the first one, the 3ab minus the 2a, the only thing that I see in common there is that they both share an a in common. So I'm going to factor that out to leave over a 3b minus 2. And then on the second one, let's see, they both share no letters, but they both share a 4 in common. So I'm going to factor a 4 out to leave myself a negative 3b plus 2. Now what happens from time to time is maybe your parentheses don't match exactly. You'll notice that the only difference is that both signs are backwards. That is an easy fix. I'm not going to mess with the first one because that's already in the right format. But if I want to turn this negative 3b into positive and this positive 2 into a negative, I can change the positive 4 in the front to a negative 4, and this becomes a 3b minus 2. Because now, since both of your parentheses match, you can now factor by GCF. I can take a 3b minus 2 out front, and this a and this minus 4 are what's left over. So a minus 4, that is your final answer by grouping. Not very popular a lot, but we will see it from time to time, so make sure you recognize when there's 4 terms and you're asked to factor, it's usually going to be grouping. And then probably the most common type of factoring that you will see is when you have the basic trinomial and for 3 terms and you're asked to factor it into a pair of binomials. So we're going to do a lot of these. I'm going to try to show you a few hints here and there, but a lot of it's going to be a lot of mental math and a lot of writing stuff down. So for example, number 6 says, if you have x squared plus 10x plus 24, what does that factor into? So your ultimate goal is to factor this into 2 separate binomials. Here's kind of my little trick. Step number 1, if there's an x squared, or as we'll see a z squared on the next one, that's going to give away what your first terms are. The x and the x create the x squared. The trick is to do your mental math, or you can write it down if you'd like, you need to find 2 numbers that multiply to get positive 24, but they add to get positive 10. Whatever those 2 numbers are is what's going to go next to each of the x's in your answer. So what 2 numbers multiply to get positive 24 and add to get 10? It would be a plus 6 and a plus 4. 6 times 4 is 24, and 6 plus 4 is 10. That is your final answer. This is the more common way that we're going to do factoring, so we're going to see a lot of these. So as we go through these, if you ever want to pause the video and try them yourself before I do, go for it. Number 7 says you have z squared minus 11z plus 28. So once again, I got to figure out how to factor it into the right form. So the z squared is going to be z and z. That's usually the easy part. And then once again, can you think of 2 numbers that multiply to get positive 28 but add to get negative 11? Well, first thing you may think of is 7 and 4, and that's correct. But in order for them to add to get negative 11, it's going to have to be minus 7 and minus 4. Negative 7 times negative 4 is 28. Negative 7 minus 4 gives you the negative 11 in the middle. So very good. Just make sure you pay attention to the negatives when they pop up. All right, let's do a couple more. Number 8, x squared minus 2x minus 48. So same idea. If we're going to factor this, I know it's going to be x and x, and then just think to yourself, what two numbers multiply to get negative 48, but add to get negative 2? So kind of doing some round robin here, looks like you should be getting a negative 8 and a positive 6. Negative 8 times positive 6 is negative 48. Negative 8 plus 6 is negative 2. This is your fully factored form. Number 9 says you have x squared plus 5x minus 14. So same idea. We're going to do our little factored form. That x squared means I have to put x and x, and then try to think of two numbers that multiply to get negative 14 and add to get positive 5. So that will end up being, let's see, you should do positive 7 minus 2. 7 times negative 2 is negative 14, and 7 minus 2 is going to be positive 5. That is your fully factored answer. So it's going to take some practice. Like I said, as we go through these, just making sure you practice, because this factoring stuff is kind of a kicker for some people. Just take your time and practice, practice, practice on your homework. All right, probably the biggest problem that I see students struggle with is what happens when you have a number in the front. So we don't do a lot of these, but I am going to show you a kind of a shortcut that may help you save some time. So when you see number 10, you see 6y squared minus 19y plus 10, and I want to factor this. Now, some of y'all may have learned different techniques. Here is a technique that I like to do. Whenever there is a number other than 1 in front of the y squared, I'm going to take this number and I'm actually going to move it over here and multiply it by the last number to make this y squared minus 19y plus 60. That way I can use the same factoring techniques that I just talked about. So if we try to factor this the same way we did earlier, it would be y and y. And let's see, to get positive 60 and negative 19, it should be a negative 15 and a negative 4. But that doesn't mean you're done. That is not the final answer. That's the answer to the one above it. But since I changed the problem, I now have to rechange it back. I multiplied by 6 to make it work. The next thing you want to do is on these constants is you want to divide them by 6 and simplify. So that's going to end up giving you y minus 15 and 6 both share a 3 in common, so dividing both of those by 3 is not what I just wrote down. Sorry. That's going to end up giving you a 2 on the bottom. And on the last one, 4 and 6 both share a 2 in common, so that would be a 2 over 3. And then if you do have fractions left over, we don't want to leave it this way. Whatever number is on the bottom after you simplify can come back to the front. So we can rewrite this as 2y minus 5 times 3y minus 2. This is your final answer. That's just a little trick that I've done a lot, and I learned it a long time ago, and I teach it whenever I teach this class. So if you want to use it, go for it. It does take a little bit of time, but it does work every time instead of you having to try to guess what the numbers are. Now, so you can see a second one, because I know maybe you're thinking, whoa, let's do that again. So let's look at number 11. You have 9x squared plus 18x plus 5, and you want to factor this. So I'm going to take that 9 in the front. I'm going to multiply it by the 5 on the end, so I can rewrite the problem. X squared plus 18x, 9 times 5 is 45. So factor this like we've done the last few problems. It would be x and x, and then two numbers to get 45 and get 18, you should get 15 and 3. And then since I multiplied by 9 to make this work, I'm now going to go back and divide both of my constants by the same 9 and simplify, which would end up giving me x plus 5/3 and then x plus 1/3. Since both of these have fractions again, whatever number's on the bottom after you simplify just comes back up to the front, and this can be written as 3x plus 5 times 3x plus 1. This is your final answer. So on every I'm not going to show all these steps on every problem, but usually I'll on the later problems, especially later on in the class, I'll just kind of jump straight from here to here. But this is what I'm usually doing. I'm usually doing it in my head a little bit quicker, but I wanted to show you the steps. That way everybody knows where I'm getting these answers from. All right, let's do a couple more. These are some special cases. So if you look at number 12, it doesn't look too bad, but let me show you what happens that's a little bit special. You've got w squared plus 12w plus 36. There's no number in the front, so you don't have to rewrite anything. But when you go to factor this, you're going to notice that something nice happens. The w squared means I can do w and w, and then two numbers that multiply to get 36 but add to get 12 are actually the exact same number, plus 6 and plus 6. Now, while you can leave it in that form, a way that I want you to start noticing is that, remember when we did all the FOIL stuff in the last video, this is the same thing as w plus 6 all squared. It's just a more common way to write the notation, and that's the way that I will write it going forward if the terms do match. All right, number 13 is actually an example where you have to combine multiple rules. Now, I know you're thinking, oh, there's a 3 in the front. Let me go ahead and move it over and do that little trick you showed me. Well, hang on a second. Before you do that, something that may make it a little bit easier is that the 3, the 30, and the 75 actually all have a greatest common factor. So I would actually recommend you do that first. That didn't happen on the last two problems we did, but it does happen here. If I take a 3 out of all three of those terms, it leaves an x squared, then a minus 10x, and 3 goes into 75, oh, let's see, 25 times. Now, this part becomes a lot easier to factor. So if I leave the 3 out front, I can now factor this the same way I've done most of the problems today. That would be x and x. And then to get multiply to get 25 and add to get negative 10 is going to be minus 5 and minus 5. But since both of those are the exact same thing, this is the same thing as 3 times x minus 5 all squared. So just a couple special cases that we'll run into from time to time, but there is a couple more factoring problems. All right, so now moving on to those special cases. I mentioned in the last video that the difference of squares would show up again. Well, here it is. This time, though, you don't want to expand it. You want to use it to go backwards into a factoring technique. So in the last section, we went from the a minus b times a plus b to the a squared minus b squared. Now I need you to go this direction. We can say that a squared minus b squared factors into a minus b times a plus b. So to get the a and the b, you have to notice that both of your terms are squared powers and they're being subtracted. So what you'll see me do, and I'll actually work it out later on in the problems, is that we're going to do square roots to figure out what a and b are. But this can also be projected into the cube world as well. So we're going to see two other formulas. One of them is called sum of cubes, and one of them is called difference of cubes. If you have two terms that are cubed and they're being added together, they can be factored into the formula a plus b times a squared minus ab plus b squared. And then similar, if you have two cubed terms being subtracted, they can be factored into a minus b times a squared plus ab plus b squared. Now on both of these, in order to figure out what a and b are, square roots are not going to be helpful. So instead, we're going to take the cube root of those to figure out what a and b are. So let's use those three formulas and let me show you an example of each one. That way you know what I'm talking about. So number 14 here says, if you have x squared minus 121, what is the factored form? Well, the first thing I notice is that you have an x squared. So I'm actually going to note that as my a squared term. That means that the 121 has to also be a squared term. So I'm going to call that b squared. And since they are being subtracted, we can use the formula that a squared minus b squared factors into a minus b times a plus b. To get the a and b that you need, I mentioned square roots on the last slide. Well, that's what I'm going to do. I'm going to take the square root of both terms. The square root of the x squared gives me x, and the square root of 121 gives me 11. These are the two numbers that you have to plug in for your a and b. So a is going to be x, b is going to be 11. So I can write this as x minus 11 times x plus 11. And that is your final answer. Now, while those are a lot more common, not as common as the cube stuff, but I still want to run through this with you. On number 15, you have an x cubed plus a 125. You'll notice that you have an x cubed. So if I call this my a cubed term, and I call this my b cubed term, since they are being added from the last slide, we can say that a cubed plus b cubed is a plus b times a squared minus ab plus b squared. To find a, I'm not going to do square roots. Instead, you're going to do the cube root of the first term. So the cube root of x cubed is x. And to find b, you're going to take the cube root of the number, which is 125. Take the, which is 5. I should actually answer it. So I'm going to take the x and the 5, and I'm going to plug them into this factored form. So I'm first going to add them together. So that's x plus 5. Then I'm going to take a squared. So if I square x, that is x squared, minus multiply them together. X times 5 is 5x. And then plus b squared, so 5 squared is 25. This is your factored form. All right, and then very similar on number 16, I'm going to try to squeeze it down here at the bottom, is that since this first term is cubed, that means that we're going to be able to write this as a cubed minus b cubed, which has a slightly different formula, because now you're going to do a minus b times a squared plus ab plus b squared. All right, to find my a, that one we kind of already did, but I'll do it again. You're going to take the cube root of the first term. So the cube root of x cubed is just x. And for b, you're going to do the cube root of the 64. So what times itself 3 times gives you 64? That would be 4. And then I'm going to plug the a and b into my factored form. So you should end up very similar to the purple part, x minus 4 times x squared plus 4x plus 16. This is the factored form of that difference of cubes. So those are 3 formulas that we will see. Definitely the first one's a lot more popular, but make sure you note the second and the third one because they will show up from time to time. All right, so that ends section R.6. That's kind of a review on factoring. So to wrap up chapter R and wrap up the review material, I want to go over the idea of rational expressions with you, which is going to involve factoring again, but it's also going to involve a few more steps after you finish factoring. So first thing I want to see if we can do is I want you to simplify each of these rational expressions and make sure you're careful about the values that are restricted. All right, so on number 1, the first thing you want to do is you want to talk about the restrictions. When you have a fraction involved, whatever is on the bottom cannot be 0. So since 5 plus x cannot be 0, just ask yourself what number makes that 0? Well, that would mean that x can't be negative 5. So on your homework, if they ask for the restriction, that's what they're asking for. As far as the simplifying goes, they want you to factor what you can. If you look, the 5 plus x, there is no way to factor that, so we're going to leave that alone. But the x squared minus 25 is your difference of squares formula that we just covered. So you will be able to factor that into x plus 5 times x minus 5. Now the good thing with addition is that it doesn't matter what order you add stuff in, it's all going to be the same. So when you see an x plus 5 over a 5 plus x, those are actually the exact same thing no matter which way you add them. Since they cancel each other, you are only left with an x minus 5. So that is the simplified form of this rational expression. Number 2 looks very similar, but it does have a trick in it, so I wanted to run through this with you as well. So once again, getting your, if it asks for you to find your restriction, remember the bottom cannot be 0. So if you know that negative 7 minus x cannot be 0, what can x not be? Well, if you do a little bit of rearranging, you could say that x cannot be negative 7. Because if you plug negative 7 in, negative 7 minus a negative 7 goes to 0, so that is your problem. So that is your restriction. If you factor this, actually the top and the bottom both factor. The top factors the same way the first one did. It's a difference of squares. So it would be x plus 7 times x minus 7. And on the bottom, there is a greatest common factor. They both share a negative in common. So if I factor, we'll say a negative 1 out, that gives you a positive 7 and a positive x. And as we can see, x plus 7 and 7 plus x are the exact same thing. So you are left with just an x minus 7 on top and a negative 1 on the bottom. So if we divide this negative 1 into both terms, this would be x over negative 1 minus 7 over negative 1, which simplifies into a negative x plus 7. You essentially just change the signs of both terms on top. So that's kind of the idea for this section. We're going to have a few more complicated than this, but we have to simplify these rational expressions. All right, so let's do some more. The restricted values, we'll talk about those along the way, but if you look at number 3, you have 2x squared minus 9x minus 35 over 2x squared minus 7x minus 30. Now, if you need to, when you go to factor these yourself on your homework, you may have to stop and do that little shortcut I showed y'all in the last section. But to save a little bit of time on these videos so that they don't run for a couple hours long, I'm going to actually just factor these in my head, and then you can leave that for you to practice on your own. So when you see the numerator here, we can factor the 2x squared minus 9x minus 35, so do a little bit of work. And you should have a 2x and an x when you're done. You should have, let's see, I think it's a 7 and a 5, and it should be minus and then plus. So after your work, you should get that to be 2x plus 5 times x minus 7. And then doing the exact same steps on the bottom, if you were to factor that, it would be, let's see, 2x and x. It would be 6 and 5, and then plus and minus. So the bottom would factor into 2x plus 5 times x minus 6. And as you can see, the 2x plus 5s cancel each other off. All right, and then you're left over with an x minus 7 over an x minus 6. That is your simplified answer there. So the big thing is factoring. Make sure you factor correctly and cancel off your like terms. On number 4, you've got 2 different kinds of factoring techniques. So in this one, you've got an x cubed minus 125 over 3x minus 15. Now the easier one to factor is definitely the bottom here, because the only thing that you can do is notice is that both terms have a 3 in common. So if you factor a 3 out of both terms, it makes it 3 times x minus 5. Now the x cubed minus 125, that's that difference of cubes formula I gave you earlier that said a cubed minus b cubed is equal to a minus b times a squared plus ab plus b squared. So in this case, we could say that a is the cube root of x cubed, which is x, and b is the cube root of 125, which is 5. It's actually, we saw one very similar to this earlier, but it's just a difference this time. So plugging your a and b into this factored form would be x minus 5 times x squared plus 5x plus 25. And as you can see, x minus 5 divided by x minus 5 cancels, and this gives you an x squared plus 5x plus 25 all divided by a 3. And that is your final answer. So when you're doing this homework for R6 and R7, please make sure that you are practicing your factoring, because factoring is not going to go away anytime soon. So you have to be comfortable doing all of this. All right, so we're going from simplifying, and now we're going to start doing operations. So on number 5 is our first example of multiplying. You've got 6x minus 15x squared over 16x squared plus 8x plus 1 times 4x squared plus 5x plus 1 over 25x squared minus 4. So the good thing with multiplying is that there's not any tricks here. The only problem is going to be, once again, I keep telling y'all, you're going to have to be able to factor everything yourself. So all 4 of these terms factor in some way. So go through, if you want to pause the video and try yourself, go through and factor all of these out, and let's see what we can cancel. All right, so on the top left, I notice that they both have a GCF in common. We can take a 3x out of both terms on top, which will leave me with a 2 minus 5x left over. On the bottom left, you can factor that using your techniques, and you should be able to get that into 4x plus 1 times 4x plus 1. On the top right, if you factor that one, it looks like you should get, let's see, a 4x and an x, then a 1 and a 1, and a plus and a plus. So it should factor into 4x plus 1 times x plus 1. The bottom right is a difference of squares, so that's going to actually factor into a 5x minus 2 and a 5x plus 2. So first thing you look for is, do you see anything that cancels right away? Well, one thing, 4x plus 1 over 4x plus 1 cancels. And then I see one that's very, very close. The 2 minus 5x and the 5x minus 2 are very, very close to each other. But since they are not addition, you cannot just cancel them because they're close. Since they are subtraction, you will need to make one of them backwards from what it originally is. So what I'm going to do is on the top here, instead of it being 2 minus 5x, you can rewrite that as 5, oops, not as that, sorry, wrote down the wrong thing. Ignore that. So give me a second to erase that. There's not a good eraser on this device I'm using. So if I flip-flop, that's going to end up being 5x minus 2. You can do that as long as you bring a negative out front. So I'm going to write that as negative 3x. We canceled one term already, so we have another 4x plus 1. There's still an x plus 1 on top, and then I'm not changing anything on the bottom right. 5x minus 2 times 5x plus 2. But now I can easily see that 5x minus 2 and 5x minus 2 cancel, and once everything is canceled off, just put it together. You'll have a negative 3x and an x plus 1 on the top of your fractions, and on the bottom you have a 4x plus 1 and a 5x plus 2 multiplied together. You don't need to FOIL, you can leave it in factored form, but there's an example of where you are multiplying 2 rational expressions together. Once again, factor, factor, factor. That's the name of the game in this section. Let's do a second one with multiplication, and then we'll go on to something else. You've got x squared minus 9 over 15 being multiplied by x squared plus x minus 12 over x squared minus 6x plus 9. Once again, with the multiplication, what I'm going to go through and do is I'm going to go through and factor anything that I can. Now, I guess a little bit of good news here is that one term doesn't factor. That 15, you can't factor just a number, so we're just going to leave the 15 alone. But I believe the other 3 all factor in some way. The top left, the x squared minus 9, is a difference of squares, so that will factor into x minus 3 times x plus 3. The top right and the bottom right are just basic factoring, so that's going to end up being x plus 4 times x minus 3 for the x squared plus x minus 12. And for the x squared minus 6x plus 9, it should factor into x minus 3 times x minus 3. So what cancels? Well, x minus 3 over x minus 3 cancels. Another x minus 3 over x minus 3 cancels. And you are left with an x plus 3 times an x plus 4 on top, all being divided by just a 15. A little bit easier that time. Like I said, they're not all ridiculously hard. Some of them will be harder than others, but the big thing is, once again, I'm going to keep saying it until this video is over. Make sure you factor correctly and cancel off your like terms. All right, so for the first time, we are now going to look at a division problem. So the good thing is division's not too bad. It just requires you to do one extra step. When you are asked to divide multiple rational equations like this, I'm going to go back to the idea, and maybe you remember, maybe you don't. I call it the KCF method. It's called keep, change, flip. You want to turn this division problem into a multiplication problem because it will make it easier to simplify. So the first thing I'm going to do is not factor, is I'm going to rewrite this problem. The K stands for keep. That means you do not have to touch the first fraction. Leave it exactly as it looks. You are allowed to change the division to multiplication, but to do that, you have to now flip over the second fraction and make it x squared plus 14x plus 49 over 3x squared plus 24x plus 21. That's the only thing. Everything else is now going to work the same as it did the last two problems. Factor all of this and then simplify by canceling off your like terms. Looks like some of this factoring is going to take more than one step, so we'll just kind of do a couple steps here. So let's see, we have a fraction times a fraction. All right, starting on the top left, you can factor that into x minus 7 times x plus 1. Now the bottom left will take two steps. Number one is that both 2x squared and negative 98 both share a 2 in common. So if I take a 2 out of both of those, it becomes 2 times x squared minus 49. On the top right, that one's just a regular factor, one step. It factors into x plus 7 times x plus 7. The bottom right's very similar to the bottom left because the first thing I notice is that all of those terms have a 3 in common, which makes it x squared plus 8x plus 7. Now you got to keep factoring. The bottom two terms factor a little bit further, so let's do that. This will be x minus 7 times x plus 1 over 2. X squared minus 49 is a difference of squares, so it factors into x minus 7 times x plus 7 times, so we're not going to, the top right's done, so we'll leave that the same. On the bottom, you have the 3, and then x squared plus 8x plus 7 becomes x plus 7 times x plus 1. Go through and cancel any like terms. There's a lot of them here. X minus 7 over x minus 7, x plus 1 over x plus 1, x plus 7 over x plus 7, x plus 7 over x plus 7. Literally everything cancels except for a couple of numbers. Since everything on the top canceled, we use an understood placeholder of 1. On the bottom, you have the 2 and the 3 left over that you can multiply together, and that's 6. So this ugly fraction up here actually simplifies all the way down into a constant of 1 over 6. All right, subtraction. So we did division, addition, subtraction. This is the one that you may not always be able to go directly into because in order to add or subtract fractions, you have to have the exact same denominator. Now on number 8, I wanted to show you an example of what you're looking for. You're looking for something like this. You notice that both denominators are x minus 7. So since they match exactly, you are allowed to make this one big fraction, where the denominator will be x minus 7, and the top part is what you have to combine. So you're going to have the x plus 5, and you're going to subtract the 3x minus 4. So on the top, if you multiply that negative through, it's x plus 5 minus 3x plus 4, all still divided by x minus 7. Then you combine your like terms on top. So x minus 3x is negative 2x. 5 plus 4 is 9, all over x minus 7. Now that was very nice because the denominators were already the same, but a lot of the problems that you're going to see for the rest of today is that maybe they aren't the same. Look at number 9, for example. You have 7 over 12x squared y minus 12 over 4xy. So what I usually do if I'm a student or if I'm teaching this class is that I'm going to break it down. Do step by step. One thing that will not change is that you cannot get rid of the 7 and the 12 on top. But here's what I'm going to do. Let's break it down into 3 parts. Number 1, 12 and 4. Since both of those can go into 12, I'm not going to change the 12 on the bottom of the first fraction, but if I change that 4 to match that 12, you have to also fix the top. So what did we do? Well, I multiplied by 3 to make 4 into 12, so I have to also put a 3 on top. When it comes to the x's, you have an x squared and an x. I usually just say whichever one's bigger is the one you want to do. So I'm going to put an x squared on the bottom of this fraction and an x squared on the bottom of this fraction. I did not change this first fraction, but I did change the x to an x squared by multiplying by an extra x. So you got to also put that on top. The y, they both already match. Since they both already have the same y, nothing's going to change there. I'll just rewrite them. So what are you left with? Well, the first fraction actually didn't change at all. It's still going to be 7 over 12 x squared y minus, and while you now have a 12x squared y on the bottom of the second fraction, multiply these 3 together to get your new numerator. 12 times 3 times x is going to give you 36x. Now you can put this together as one big fraction that has a 12x squared y on the bottom, and then if you put the tops together, they don't go together because one's a number and one's an x, so your final answer is 7 minus 36x over 12x squared y. All right, so let's do another one. What happens when you start doing binomial differences? So something like number 10. 7 over x minus 3 plus 4 over x plus 5. So while this is going to look a little bit different the way I do it, it's actually the exact same thing we just did. I'm going to rewrite this into 2 separate fractions. Now the 7 on top and the 4 on top don't change. And actually, this one's actually a little bit easier to follow along. This x minus 3 on the bottom. Since there is an x minus 3 on the bottom of the first fraction, I have to also put an x minus 3 on the bottom of the second fraction. But since it wasn't there originally, I have to also add it to the top in order to keep it equal. That's actually the same with the x plus 5. Since the x plus 5 is already on the bottom of the second fraction, I have to also put it on the bottom of the first fraction, which means I also need an x plus 5 on top since it wasn't originally there. So what you can do now is you can put this together as one big fraction. So you have an x minus 3 and an x plus 5 as your denominator. On the top, you have a 7 times x plus 5, and you're going to add to that a 4 times x minus 3. If I multiply the top out, that's the only part I'm worried about, you should get a 7x plus 35 plus 4x minus 12, still being divided by x minus 3 times x plus 5. And if you combine your like terms, you should get an 11x plus 23 on top, and you still have the x minus 3 and x plus 5 on the bottom. So there's an example where, once again, you can add the two fractions together as long as they have the exact same denominator. That may require you sometimes to adjust them, as we've seen on the last two examples, and that we're going to see on the next few as well. All right, we haven't done an addition or subtraction problem with factoring, so let me do one of those for you. Number 11 says you have x minus 8 over x squared plus 12x plus 27, and I want to subtract from that x minus 9 times x squared minus 9. Well, since this one's going to require you to factor some stuff, let's do that first. Don't worry about common denominators. Just factor what you can. So the x minus 8 is not going to change, but the bottom of the first fraction should factor into an x plus 9 and an x plus 3, minus on the top of the second fraction, the x minus 9 doesn't change, but you can factor the x squared minus 9 into a difference of squares, which is x plus 3 times x minus 3. Here's where you have to make the denominators match. So we got two big fractions here. Remember, the x minus 8 on top of the first fraction and the x minus 9 cannot go away. And what you probably notice is that both denominators already have an x plus 3. So I'm actually going to go ahead and put an x plus 3 down on both because that's not changing. Here's where they don't match. The first fraction has an x plus 9 on the bottom, which means I also need an x plus 9 on the bottom of the second fraction, which means I have to now add an x plus 9 on top of the second fraction to keep it equivalent. Likewise, the second fraction has an x minus 3 on the bottom. The first one does not. So if you add the x minus 3 on the bottom of the first fraction like you have to also add it on top to make it equivalent. So what does that leave left over? Well, this now leaves one big fraction, and it doesn't matter what order you write these bottom numbers in. I'll just keep them in the same order. It's x plus 3, x plus 9, x minus 3. And then you're going to have to do some foiling. So you're going to have to FOIL the first term. So x minus 8 times x minus 3 is going to give you an x squared minus 3x minus 8x plus 24. Then you have to subtract from that, multiplying the x minus 9 times x plus 9. Now that's the difference of squares, so if you remember from the first video, you can actually just write that as x squared minus 81. Continue cleaning up the numerator here. So you should have an x squared. The x's go together to make a minus 11x plus 24. Distribute that negative through to both terms, which is minus x squared plus 81, all over the same three terms, x plus 3, x plus 9, x minus 3. And last but not least, combine your like terms, which for the first time, this is even better. Your x squareds go away. But you have to also notice that the negative 11x comes over, but you can also put together the 24 and the 81, which add together to give you 105. And as you've seen through the last few problems, these denominators are not going to change because you forced them to be the same. So those don't change. It should be x plus 3 times x plus 9 times x minus 3. This is your fully simplified answer based on the subtraction. All right, and then to wrap up this section, we're going to look at a couple of complex expressions. So one last problem that we're going to run into from time to time is what happens when you have a fraction inside of a fraction. Well, your job is to get rid of it, and here is the easiest way to do that. On example number 12, you have a 5 minus 1 over x divided by a 5 plus 1 over x. Your job is to get rid of those x's. If they are both the same thing as they are in this first one, all you have to do is multiply the top and the bottom by what that is, which is x. And you're going to take these x's and you're going to multiply x by all 4 terms. So x times 5 gives you 5x minus x times 1 over x over, on the bottom, x times 5 is 5x plus x times 1 over x. And as you can see, x divided by x and x divided by x cancels, as it should if you do it this way. And you have a final answer of 5x minus 1 over 5x plus 1. That is your final solution. Now, once in a while, you may have different small fractions. So as you can see on number 13, it is 1 over x minus 7 over 1 over x squared minus 49. So while there are 2 little denominators you have to get rid of, if they are not the same, I usually just pick the bigger one because they're pretty close. X and x squared are similar. In this case, I'm going to pick the bigger one, and I'm going to multiply the top and bottom by x squared. So multiply x squared by everything. That's going to give you an x squared times 1 over x minus 7x squared over x squared times 1 over x squared minus 49x squared. The bottom one's the best because x squared over x squared cancels, but on the top, while this x cancels, you still have 1x remaining outside the parentheses. So you end up with an x minus 7x squared over a 1 minus 49x squared. And here's the other kicker to this. While the top one does not factor, this one factors and you can keep going. If you look at the top, they both share an x in common, so you can factor an x out to make it x times 1 minus 7x. And on the bottom, that is actually a difference of squares, and this factors into 1 minus 7x times 1 plus 7x. But as you'll see, you now have 2 terms in common that you can cancel more of. That's great. And you're left with a final answer of x on top and a 1 plus 7x on the bottom. That is your simplified complex rational expression. And last but not least, to wrap up this video and to wrap up chapter R, what if you have 2 denominators but they are not both x's, or x and x squared? So number 14, 4 over x plus 7 over y divided by 7 over x minus 4 over y. Your job is to get rid of all of these denominators by multiplying the top and bottom by something. On the first example, we did x because they matched. On the second example, we did x squared because it was very similar. But if they are completely different, when in doubt, multiply by both. So I'm going to multiply everything by not only the x, but also the y. So when I write this out, so we're going to multiply these 2 terms by everything. That's going to be x times y times 4 over x plus x times y times 7 over y divided by x times y times 7 over x minus x times y times 4 over y. And while everything's not going to cancel, all of your fractions should still cancel. So starting on the top, you see you have x divided by x, then you have y divided by y, and these are all just canceling. X divided by x on the bottom, y divided by y on the bottom. So what do you have left over? Well, starting on the top, you have a y times a 4, which is 4y. You have an x times a 7, which is a plus 7x, over a y times a 7, which is 7y, minus an x times a 4, which is a 4x. There's nothing else in common. They don't all share a number or a letter in common. So actually, you are completely done with this problem. It just looks a little bit different because you had to multiply by an x and a y. So that ends this video on sections R6 and R7. That also ends chapter R, which is the review material. In the next video, we are going to start chapter 1 and start looking at solving equations for variables.